Swayam Prabha. Digital India. Educated India.
This maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory is a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar lecture theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio-visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar.
Hello everyone, welcome to lecture 32 of the course Marine Renewable Energy Systems, Analysis, Design and Development. I am Dr. Basangoda I. Patil, Assistant Professor, Department of Civil Engineering, PDU, Gandhinagar, Gujarat. So in this lecture, we will see the numerical modeling of one of the novel floating wave energy converter and also a multi-utility floating platform called TSUSUCA Dolphin, which is conceptually developed and modeled and analyzed using a numerical tool called ANSYS Aqua. This is a bio-inspired floating platform. Why bio-inspired? Because it resembles the shape of a dolphin. Not only just the shape, it also takes the advantages of the function what dolphin or aquatic animal have, such as the drag reduction ability. So both function and form is imitated here. Then we can call this model as bio-inspired model. So the word TSUSUCA is a coined word here. It is abbreviated like this: tsunami protection, solar power utilization and coastal applications. This word is applied and granted with a trademark. Number is as shown, and the floating platform as a whole SUSUCA Dolphin is patented, and the Indian patent number is also shown here. And this floating platform has multi utilities, such as it can primarily it will produce power from sea waves with high efficiency, and it offers a tsunami protection. It will generate power from solar panels. Then it can act as a recreation and tourism center, and it will provide training for seasickness. So, all these multi utilities make this floating platform as a novel multi utility floating platform. So, various parts of this floating platform are: main is a dolphin shaped body, which is having head, central body and the tail, and the nose of it rests on the floats here, and there is a bottom flap to arrest the waves, and then the bottom tail will have hinged connection, and that hinged connection will be between the bottom tail of the dolphin body and the fixed base block, also called as deck. Then the top end of the tail can be used to connect to a PTO, and that PTO will be mounted on the fixed base block, and complete the body of the dolphin will float on the surface, ocean surface freely, and this base block will be on the shore, and which is fixed structure, and the dolphin is connected to the base block with hinges. The various working modes of this SUSUCA dolphin are shown on this slide. The first one shows the side view, which is having all the parts. Under the action of wave, dolphin will move up and down. This up and down motion will create the linear motion, which then further is harvested and utilized by the linear PTO to harvest wave energy and to produce electricity. And further, another PTO can be connected to the same dolphin model by replacing linear motion electricity generator LMEG PTO. We can replace it with hydraulic PTO, and the hydraulic components and other parts are also shown here. And under the extreme waves, when the extreme wave hits the front side of the dolphin, the body will lift and stand more or less vertical like this, and it can reduce the flooding behind its body and by protecting the important structure if any. Then once this particular SUSUCA dolphin is successfully deployed, and many such bodies can be tandemly placed and mounted on the base block, fixed base block. When all are working together during the power generation, they can be connected to the components of power generation and storage like this. So these four are the primary functions. In that, wave energy harvesting is the main function of this floating platform. Apart from this, if we can provide solar panels on the body, because this body is exposed to open air, sun, and if at all we provide solar panels or solar films, and the above body can also be utilized to harvest solar energy. And also, since this is a hollow body, dolphin shaped body, inside it can be converted into a recreation center or a training simulator for training young sailors who have the motion sickness problem. So, this whole device is modeled numerically analyzed using ANSYS Aqua, and the preliminary dimensions before we started our modeling are fixed based on the suggestions by Chandrasekaran et al. In 2022. By trial and error, the dimensions are fixed and the device geometry and working principle are shown here. First, the total length, overall length of the dolphin shaped body is 32 meter, and the width or depth of the body varies like this: 2.88 meter in the front, and in the middle it is 5.77 meter, and near the tail it is approximately 4 meter. And the deck's length considered for this study is around 14.7 meter, and the float dimensions, the diameter of the floats are 1 meter, and width of each dolphin is around 12 meter, and water depth considered for the study is 150 meter, and the CG, that is center of gravity of the TSUSUCA, is located here, and these black color dots indicates various connections which will be explained in the coming slides. And when the wave hits, or when the dolphin body is freely floating on the surface of the body, this particular video clip shows the freely floating motion of the dolphin shaped body, and the below clip shows how it is being lifted under the action of extreme waves, or when the wave height is more, and when such waves hits the nose of the dolphin, this will be lifted like this as shown in this video clip. First, the two-dimensional device geometry is created. Instead of directly going and modeling in the aqua, here the two-dimensional geometry is created using AutoCAD. Then it is extruded to the 3D model using AutoCAD only by appropriate dimension. With appropriate dimensions, it is extruded, and this extruded model is saved as .igs file or .iges file, and it can be exported to the ANSYS Aqua tool for the further numerical analysis. So, when the first home page of the ANSYS will somewhat look like this, it is workbench. When we type workbench, once the software is installed, we get this one, and from this we pick the geometry option from the many options which are available on the left side. So, geometry is picked, and then the option here called as geometry, when we right click on it, we will see this import geometry option, and when we browse and locate the 3D model which is saved in these two formats can be imported. Once it is imported, it will take us to design modeler module. This design modeler module will help us in locating the origin, which is fixing the origin, because from the origin itself the centroidal coordinates and other dimensions are marked. When this is very important, fixing the origin is very important to give the point mass and mass moment of inertias in the further steps. And then Aqua will not analyze a solid body, it will analyze a thin surface body. So, whole dolphin shaped model here which is shown, which is having two dolphins side by side in tandem, which are connected to the fixed deck. They all are converted to thin structures by selecting thin option here and giving the appropriate zero thickness, because initially some thickness will be there by default, we have to make it 0, and then the thin surfaces are obtained. Then we have to slice. Okay, this is a thinning surface what I was speaking, and here we have to make this thickness 0, then the green color tick mark should appear, then only it is understood that thinning is completed successfully. Then further we move on to next option is called as slicing the geometry. This is important to differentiate between the draft and the portion above the water level. So, here this line indicates the sliced plane, that means below this submerged part, above is the freeboard. That is done like this: select slice option, then select slice type as slice by plane, and we can select xy plane because that is the plan mode, xy plane. We can select xy plane. Then when we click on generate, always once any option we select in ANSYS Aqua, after giving necessary dimensions and necessary actions, we have to click on generate to get this green color tick mark. Then once we generate, slice the model is sliced, okay, and the various parts available after slicing are displayed here. Then before moving to hydrodynamic diffraction module to get the necessary free float RAOs and other results, we have to give the masses and mass moment of inertia to the model. So, to do that, we have to extract CG coordinates and mass moment of inertias. How? Using static structural module. In the Aqua, on the left side option here, we can find the static structural option, then that can be linked to the geometry like this, and the geometry or model which is there here will get linked to the geometry of static structural. Then when we double click on the model, it will take us to the workspace, inside workspace for home screen of the static structural tool. Here geometry is imported. Then since there are two dolphins, body 1 and body 2 are available here, and in the body 1 it is sliced. So, therefore, the freeboard and the draft both are marked as body 1 and body 1 here. So, we have to select body 1 and give some thickness here. This thickness is the actual thickness what is there in reality. For example, whole dolphin, TSUSUCA dolphin will have some thickness which is made up of maybe steel structure, and it will have some thickness. That actual thickness is given here, and the static structural or appropriate material is selected, that is the material option. All are here in this option. When we scroll down here, we first find out thickness, we have to enter the appropriate thickness here. Then when we scroll down further, we see this material option where the material is selected, and here we have selected static structural. Then once the appropriate thickness is given, the coordinates of the centroid CG are displayed here. We can note down these coordinates: centroid along x, along y, and along z. Then IP1, IP2, IP3 here indicates the mass moment of inertias. So, all these are noted, and we will enter those values manually in the further steps. So, once these are noted, we will take hydrodynamics diffraction module again, which is available here in the left side options. Many options are available. We have to find this hydrodynamic diffraction module. Then we have to pick that and drop on this geometry, then it will get linked to the geometry. Then when we double click the model, it will take us to the home screen of the hydrodynamics diffraction module, where it is very important to give the point mass before we start the further steps. But before giving, when we click on the geometry, it will ask us what is the water depth, and you can give the water depth here, and then water density, and then acceleration due to gravity, then water size along x and y. So, all these are inputs required, we can alter them. Then once this is done, next we can see the body 1, body 2 and deck which are imported in the hydrodynamic diffraction module. On the body 1, when we click on right click, when we click it and click on right click, we will see option called as add, then we will see point mass, and this point mass When we select, this will take us to the dialog box where we can change this mass definition to the manual definition option. Then we can give the centroidal coordinates what we have noted down before from the static structural option. Then further, this also we can change by using the drop down arrow mark. You will see the drop down arrow mark when you start using the tool. You can see you can select direct input of inertia, then where your IXX, IYY, IZZ can be imported, and these radius of gyration values KXX, KYY, KZZ will be automatically calculated as soon as you enter the corresponding moment of inertias. Then, as I told, the dolphin shaped body is connected to the fixed deck with the help of hinged connection. So, how many connections are there here? So, each dolphin will have one hinge connection. Here in this model, in this lecture, we are seeing on the screen there are two dolphins connected to one deck. So, that means two hinges will come between each dolphin, between the dolphins and deck. Then deck, I said deck is fixed, it is restrained from the motion in all the 6 degrees. So, that means there will be a fixed connection between the bottom of the deck and the earth. So, we have to give that connection also. Total mainly 3 connections are important here. One is connection 1 between dolphin 1 and deck, connection 2 between dolphin 2 and deck, and connection 3 between the deck and the ground. So, when we click on the body 1, then right click, we will say add option, then there is what called as connection point, and this connection point will help us in giving the creating the connection point. And when you choose this connection point, it will take you to this dialog box where you have to enter position of the coordinates. That means where exactly you want your first connection point, and this connection point coordinates are calculated from the origin. That is why in the beginning I told fixing the origin is very important. From the origin all these connection points are assigned. Then once the connection points, required connection point is assigned, it will be visible like this. There is a black color dot we see between the body 1 and the deck. So, that black color dot what you are seeing is the connection point 1. In short, it is CP1. So, the coordinates are mentioned here. Similarly, we can give the connection point 2 and connection point 3 with the same procedure. Then once the connection point is given, means 3 connection points are given, then we need 3 fixed points to connect them. CP1 fixed point 1, CP2 fixed point 2, CP3 fixed point 3, and all those fixed points are defined like this. There is option called fixed points, and 1, 2, 3 are already used for CP1, CP2, CP3, and it will continue the next number here. So, fixed point FV4, FV5 and FV6 here. So, fixed point coordinates are also given. These are also with respect to CG only, or with respect to not CG, origin what we have defined. Then fixed point is also visible here, and whereas in the previous slide we saw connection point CP1, it is which this is on the body 1. So, then this is a fixed point FP1 which is on the deck, Next, connection point is given by choosing the appropriate type. That means how many different types are there in aqua. We can see ball joint, we can see universal joint, we can see hinged joint, we can see fixed condition. So, all these different boundary conditions are there, they are restraints here. So, we can go to details of the joint when we click on joint 1 here. After defining connection point 1 and fixed point 1, and connection point 2 and fixed point 2, and connection point 3 and fixed point 3, we have to click on this joint 1. This joint 1 will ask which point to which point you are connecting and with what type of connection. The type is selected here. So, we have selected universal here, universal joint is selected, and then later the particular degrees of freedoms are deactivated in order to get only the required pitch motion between the body and the deck, because under the action of the waves the body should lift like this. So, this pitch is only activated by arresting roll and sway and other unnecessary or not required degrees of freedom, that I will explain in the hydrodynamic response module step. Then once these connection points are assigned with the proper type with the fixed points, we have to mesh the model. And before meshing, I told connection point and fixed points with universal joints, and deck has to be connected to the ground with fixed point only. There is no universal joint selected between the deck and the ground. So, the connection point 3 at the bottom of the deck and the fixed point 4 on the top of the ground are connected with the help of fixed point only. So, this is CP3 at the bottom of the deck, and say on the ground. So, this is fixed point 6, both are connected with the help of fixed connection only. That means they should be rigid. So, then further we will go to meshing. This is very important option. So, with the appropriate meshing, we have to mesh the models. Here, since deck is larger in dimension compared to the body, and we are not that interested in the results of the deck, we are concentrating or focusing on the results of the floating body. So, deck is meshed with the coarser mesh size, and these two dolphins are meshed with the finer mesh size, and the meshing option is here, and you can give the mesh size for all the three bodies, body 1, body 2 and deck, and they are here. Maximum element size you have to enter, this is the enter, and when you enter the appropriate mesh size, you will see total nodes, total elements created here after meshing. Then once meshing is done, we will now analyze it. So, before analysis, you have to go to analysis settings and turn on this option, very important option, which will remove unnecessary errors, which will violate unnecessary errors. Ignore modeling rule violations. It will be by default no, you have to make it yes. Then further options are chosen. Then structure selection option, you have to choose the required selection. If you are interested in seeing the results of body 1, you select body 1, say if I can call it as body 1, body 2, and this is deck. And if you want to see the results of body 2, and you can go and choose body 2 in the structure selection, and if deck you are interested in seeing the results, and go and choose deck. So, that is how we can change the selection of different structures which are involved in the analysis. Then further the options to see the results, we can right click on the solution. Here we see the option solution, then insert result, then structure motion, RAOs, like this many options are there. Free float RAOs, select the appropriate results what you want, and then run the analysis. You will get the free float RAOs plot that I will show in the coming slide. And then further, when you go to the same solution option and right click on the insert result, and then select the radiation coefficient, you will see radiation damping and added mass results here. You can select them, those also if required, then run the analysis. Once you run, the free float RAOs obtained for this particular model one is shown here, and you can always import these results to Excel sheet by or .csv file using this option. Then further required results are exported like this, and they get saved to your system, and you can convert .csv file to normal Excel file, where you can plot these same plots like how you want. Then further, hydrodynamic response module we are entering now to do the time history analysis or frequency domain analysis. Here on this particular dolphin model, time domain analysis is done. So to get the response, time response, we are entering now to the hydrodynamic response module. This hydrodynamic response module is again found in the left side option only. You can choose this left side option, then link that to the hydrodynamic diffraction module here, like this, pick and drop on this model, then all these three will get linked. Then the same analyzed model in the hydrodynamic diffraction model will be linked to the response module, and you can double click on it, the model. So it will take you to the workspace of the response module, hydrodynamic response module, where the first step is analysis settings, where you can see these options, what kind of computation type you want, time response, there will be a drop down arrow mark here, drop down arrow mark, which when you click you will see time response analysis, frequency domain analysis, and many other options which are inbuilt, and then you will see what is the analysis type. Right now irregular wave response is selected. You can also change it to the regular wave response if required. So now then further inputs required are the total duration for which you want to run the analysis is selected, and the time step. You have to select the time step also, start time. If you choose time step, it will calculate other necessary values automatically. Then the I was telling deactivation of degrees of freedom. So you will see, you are seeing this deactivated freedom option, no? That is required, because initially we gave here between body 1 and deck and between body 2 and deck, both are universal joints. This is also a universal joint. I do not want the dolphin model to roll there or yaw or heave or surge and sway. I want only it to behave like this, that is pitch mode. In pitch mode it should move, and in the beginning at the tip heave is activated under the action of wave, and then further it is moving like this, that means it is a pitch. So here heave and pitch both are coupled. So only this motion I want, other things should be deactivated. So this deactivated degrees of freedom will help us in doing or deactivating the not required degrees, right. Then before we go to the time response analysis using regular waves and irregular waves, we can carry out free decay analysis to calculate natural frequencies and time periods of this model. So how it is done? So there is option called computation type. Here you can select time response analysis, and in the analysis type I told many option will be there in this drop down arrow mark, irregular wave response, regular wave response. Then you choose regular wave response, then you can give the time step here, 0.1 is given here. Then further by right clicking on the hydrodynamic response option, you can insert the manual force, that is structure force, which is a manual input. That means I am giving the unit displacement to activate the motion to get the free decay response. That means here unit displacement is not given, instead of that unit force is given, initial force is given like this and dropped and removed. Then the dolphin will oscillate like this, then the required heave and pitch free decay plots are obtained. How it is done? So we can go to manual input, then we can choose the body 1 or body 2 or deck, whichever is interested, then give the force in the required degree. For example, if you want surge free decay curve, there is a table here, this is a table. Give unit force in the beginning only, uh, in fx direction. That means fx here Newton indicates you are giving unit force like this to get surge free decay. Then Fy, give unit force in sway direction, you will get sway free decay. And Fz, give unit force in heave, you will get heave free decay curve. And similarly Mx, it is roll, and My, which is pitch, and Mz, which is yaw. So here we had given the heave unit force and the pitch unit force to obtain this heave free decay curve and pitch decay, free decay curve. This is how the free decay curves are obtained, and they can be imported to Excel also. Then the required natural frequencies and time periods are calculated. Yeah, this is what the deactivated degrees of freedom I was telling about. So, how to activate? So, select hydrodynamic response module, then click on insert, then you will see deactivated freedoms here, then select that. Once you select, there will be a option which will appear here, means dialog box. There you can select the degrees of freedom which you want to deactivate, then they will be deactivated. Then irregular wave analysis is done like this. Again, right clicking on the hydrodynamic response module, then go to insert, then irregular wave, then there are many spectra available here. So, select the interested spectra. Here John-Swap HS is selected. When you select John-Swap HS, it will ask you for the input, it will ask you for the significant wave height and gamma value, then peak frequency value. Give all these as inputs, which you will know them before only, and input them, then automatically the start frequency and finish frequency are calculated. Then further they are means once the input is created, you can analyze for irregular wave analysis. Results I will show in the next coming slides. Then how to do regular wave analysis? Just change the irregular wave response to regular wave response here using this drop down arrow mark. Change it and it will ask you what kind of wave theory or wave type. So, Ayres wave theory is used here. So, select Ayres wave theory and it will ask you the wave amplitude and the period. Give and run the analysis, you will have irregular wave analysis results. Then how the time histories are obtained? Hence, once the corresponding spectra is chosen for irregular wave analysis, we have to go to now see regular wave analysis is suppressed here. That is why there is a cross mark like this. There is a green tick mark in front of irregular wave 1, that means it indicates we are carrying out irregular wave analysis. Then after giving the necessary inputs, go to solution, then insert the result, then structure motion, structure position, then actual position. If you select all these, you will get the different time histories along surge, sway, heave, roll, pitch and yaw, different degrees of freedom. See here for this particular TSUSUCA dolphin, for various, for example, global Z body 1, that means heave body 1 and pitch body 1, heave body 2, that is global Z body 2 and global RY pitch body 2. These are the time histories obtained for this particular irregular wave given as input using John-Swap HS spectra. These are the plots, and all these plots are shown here, and they can be exported to again Excel sheet here. Directly you can export like this, or there is one more option to export all the results once the analysis is done. In the end I will show using AquaGS we can import the all the Excel sheets directly to our system. This is how the results are obtained for irregular wave analysis. Yeah, this is extracting the results by AquaGS file. How it is done? There you have to search for AquaGS option in your device, then the AquaGS will appear with the installed version and the revision number. Then the figure 1 shows the opening of AquaGS and figure 2 shows home page of the AquaGS. This is how the home page of AquaGS will appear. Then what you have to do? You have to select the graphs. Here there is option called graphs. In the above figure you have to select graphs. Then that is selected. Then you have this dialog box or home page will appear. Then you have to go to file. That file option will take you to the location where you have saved the model. So, that is where you have saved the model, where your time response analysis are saved in the form of .plt file. You have to choose .plt file here. Then once these are selected, you have to click OK. Then next, this is the folder or this is the dialog box. It will appear and you will see. Then here click on auto selection mode to select the degrees of freedom. In X direction means search, in Y direction means sway, in Z direction is heave, about X roll, about Y pitch, and about Z yaw. These are the different degrees of freedom. And position of COG means time history, how the displacement is happening or structure is moving with respect to center of gravity in different degrees. So, here in our case 3 bodies are there, body 1, body 2 and body 3. Body 1 is the dolphin 1, body 2 is dolphin 2 and body 3 is the deck. Then once you click on auto selection mode and start clicking this like this, start clicking this, they will appear here. In this space they will appear. So, that is shown in the next step. So, after selecting like this, that is what is written. After selecting all 6 degrees of freedom, the table appears as shown here like this. You are seeing position of COG in Y direction, position of COG in Z direction and position of COG about X, about Y, about Z, right. So, then structure 1, 2, 3, in 1, 2, 3, we have selected body 1, that is why it is appearing in red color. And see here also you see the difference, 1, 2, 3 are highlighted with sky blue and remaining are with different colors. That means there are no parts there, only 3 parts are there, body 1, body 2 and deck. So, that is why they are highlighted with different colors, and in that red indicates that body 1 or that part is selected. Next, once you select this one body 1 and click OK here, you will see the time histories obtained for that body 1 for all the 6 degrees of freedom. And you can have this option 1, 2, 3, 4, 5, 6 up to 9, that means up to 8, that means the results, if you select only one time history will appear, if you select two time histories will appear. So, since I have selected 6, all the 6 time histories are visible on the same screen. Then how to export this? I told in the previous slide that in the end all the results can be exported directly to our system at once. How to do that? Select all those graphs, means select by clicking like this, click on this, click on this, click on this, all these graphs you click, select, then they appear in red color, that means they are selected. Then go to hard copy, then here you will see spreadsheet.csv version or file you can export, then they will get saved to where the actual saved file is there of SUSUCA or the corresponding model. So, to reach that you have to select where you have saved the file, then go to AQW1 folder, then so first select the file where SUSUCA is saved. This is SUSUCA where the file is saved, then double click on that, then it will take you to many options. In that click on DP0, then when you double click on DP0, AQW1, AQW and AQW1 and geometry, all these files will be visible. In that click on AQW1, then in that inside AQW, then in that analysis these excels are visible now. Means in the previous step you clicked and exported all these results, 6 degrees of freedom results, they are here, and you can save them and then as a normal Excel sheet and start plotting. Then to get power spectral density plots from the time history plots, we have to follow this procedure. Select all the plots like this, all the plots are selected. Then there is option called transformation here. There is option called transformation, and click on that, right click on that, you will see time to frequency domain, time to frequency domain option. Then select this, you will see power spectral density, and this, when you click, the corresponding 6 power spectral density plots are obtained for model 1, that is body 1, in all 6 degrees of freedom, like this. Then again same procedure, select all these by clicking, simple clicking, then go to again hard copy, and you can save them in the corresponding means they will get saved automatically in the folder which was explained previously. You have to go to that folder and take those Excel sheets .csv files and save in the form of normal Excel sheets and use them for plotting. And this is how the complete SUSUCA dolphin is modeled using the numerical tool ANSYS Aqua. So further, we have conducted the experiments in the wave basin that will be explained in the upcoming lectures. So as a summary, we saw how the geometry, before geometry is drawn, that is 2D is drawn in AutoCAD, then how it is extruded to 3D using AutoCAD 3D, using extrusion command, then how the CG coordinates, how the dimensions, based on the dimensions, the CG coordinates and mass moment of inertias are obtained using static structural module. Then once the CG and static structural modules are obtained, we then entered the design modeler, to make the model thin surface and slice. Then further, hydrodynamic diffraction module is used to give the mass moment of inertias, then connection points, then fixed points, then the actual connections. And further, the free float RAOs are used or obtained from this hydrodynamic diffraction module. Lastly, we then went to hydrodynamic response module to analyze and get the natural frequencies, time periods and time histories and power spectral densities, required power spectral densities. So, in the next lecture we will see how the SUSUCA dolphin is tested in the wave basin experimentally, and how what are the different data acquisition systems are used and the instrumentations are used to obtain the results, and then further the results obtained using the numerical analysis and the results obtained using the experimental analysis will also be discussed in the next lectures. Thank you for your interest. Thank you.